Bismillahirrahmanirrahim. Dear students, I'm Dr. Asim Qureshi. Today's lecture is on divide and conquer approach, in which we are going to study two algorithms, that is quick sort and merge sort. This lecture is going to cover the merge sort only. In the next lecture, we are going to cover the quick sort. Divide and conquer approach is used to design. I'm writing for you guys, design fast algorithms in sequential computation. The strategy is that we divide our problems, then we conquer our problem and then combine. We divide our problems, and whatever the problem we have, we divide it into smaller parts, and then we conquer it, and then we combine the conquered parts of the problem. Using this approach, we are going to study two algorithms, that is merge sort and quick sort. This is basically with a reference to how we have to analyze the best case, worst case, and the average case. We can see the three analyses in the quick sort, and best case and the worst case we are going to study and the merge sort. So now let's start with the merge sort. Merge sort is basically based upon the divide and conquer approach, in which we first divide our array in two equal sub-arrays, and then we keep on doing this until we get the arrays as small as that they are doable or solvable or conquerable in our reasonable time. While conquering, we recursively sort the left sub-array and the right sub-array, because we always divide our array into two equal parts, left sub-array and the right sub-array. And after the conquering, then we go for the combine the two sorted sub-arrays into one that was required. Before moving towards the algorithm, let's do this work on some examples, so that you can understand the model of merge sort. If I were in the class, I might have been asking a few numbers from you guys, but here I'm going to suppose these numbers on my own. So let's say we have number 5, 7 random numbers, 3, 2, 4, 6, 1 and 9. Now we divide these, so this is our array. No. We divide this array into two equal parts, that is like this one and then like this one. So first sub array would be here in this part, 5, 7, 3, 2, 4, 6, 1, 9. Then we again divide this array into two equal parts. Now the size of this array is 4, so the sub arrays would be of size 2 each. So here, and again we will divide this into two sub arrays of size 1 each, and this happen with this one, the size 1, and this is going to happen with this side also. Finally we'll stop here, and we will stop at the when the sub array sizes are of size 1, because at this point all the sub arrays are sorted, because if an array has one element, then it means it is already sorted. Now we'll start merging these subarrays such that the resultant subarray or the bigger array would be a sorted one. So here, if we combine these two, and that operation is called merge in merge sort, so it will become 2 and 3. If I combine these two, so it will merge the 4 elements. So like 2 would be here, then 3 would be here, then 5 would be here. So we can assume right now, we can assume that there is some magic that is doing this thing. Afterwards, definitely we are going to do how this merge is going to take place. So 4 here and 6 here, so 1 and 9. So these are already in sorted sequence, so good for us. So now we have to merge these two. One is having 4 6, the other one is having 1 and 9, so it will become 1 4 6 and 9. And after that, we will merge these two subarrays. So one will come at the first position, then 2, then 3 from here, then 4 from here, then 5 or 6, then 5 will here come up here, then 6 or 7, then 6 will come up here, then 7 or 9, so 7 will come up here, and finally it would be 9. So our array is sorted now. This is sorted. This is how merge sort works. In order to move towards the algorithm, I would like to add the indexes of all these arrays and subarrays. So this is, its start index is 1 and its ending index is 1 2 3 4 5 6 7 8. So I will mark it here. Its start index is 1 and its ending index is 4. Its starting index is 5 and its ending index is 8. In the same way, we have marked these indices. So if I mark its start index is 1, its ending index is 1, its start index is 2, its ending index is 2. We are just marking all the indices, 1 and this is 4, this is 5 and this is 8, and this the final array is 1 index and this is the index 8. Okay, what we have done in this diagram, basically we've been doing merge sort on array A with the starting index is 1, let's call it S, and its ending index at 8, let's call it E. So we are going to we basically have sorted the array A from S to E, and not the complete array. It may be the part of the some array, so it may have few elements here, it may have few elements here. So we have performing our sorting on this index that is starting from the S and the ending at the index. Now just think about this one. What have we done on this array? Look at here, this one. So this is our array A. What we have done, we have applied merge sort on array A from S to E. So from the starting index till the ending, we have applied the merge sort here. What we have done, this isn't the same process. If we are applying the process merge sort, so are we not applying the process merge sort here? It is the very much same. It's very much same on the both sides, but the start and end points are different. So we can say that we are recursively doing the same thing, that is merge sort from applying merge sort on A from starting index. Now the what would be the starting index? Now, so basically we are applying merge sort on the left sub array and on the right sub array. Now we have to check what would be the starting index of this subarray and what would be the starting index and ending index of the right subarray. So both are the things. Now what we do after entering into the merge sort operation at any point, we basically divide the array into two parts. And the process of division is very simple, that we just chop it from the middle. That is, we calculate the middle point between the start index and the end index. So we can calculate it very easily, like m is equal to start plus end divide by 2. So we calculate it like this one. Now, so if we see at this point, the starting index is 1 and the ending index is 4. So if we calculate it like this one, so it is 1 plus 8 divided by 2 is equal to 4. So that is actually the mid value. So the starting index would be 1, the starting index of the previous subarray, and the ending index of this left subarray would be the mid. And the starting index of the right subarray would be mid plus 1, so that is 4 plus 1, 5, and the index would be the same of the previous array. The same we are going to apply here. The starting index would be the starting index of this array, that is S, and the ending index would be the middle point of this array. And then in the right subarray, the starting point would be mid plus 1 and ending point would be the same E that was of the previous subarray. Okay. If you see here, we were dividing, and then we stopped dividing when we found that the starting index and the ending index are the same. Starting index and ending index are the same. And then we continue towards the merge operation and the combining operation. So that means we are going to perform this recursive part if the starting index and starting index is smaller than the ending index. And we will write it in like this one: if s is less than end, then we will divide the array, we will divide this array, and then we will create two subproblems. And then after that, what we have to do, we will just simply merge the two subproblems because they have already been sorted, starting from index A, starting from S, from mid and end, with these three parameters. So this is the merge sort algorithm, where a big black box is still there, that is the merge operation that we are going to learn in the next phase. Now coming towards the combine operation, that is merge in this sorting algorithm. Okay. Before moving towards the exactly how it is being done in the array, so let's have a small example and then do it in that way. If I were in the class, I might have been asking you that how this can be done, that these two arrays are already sorted and we need another array, that is the third one named A. We need it to be sorted. So this process is very simple. So we can take two indices, let's say I here and j here, and we can take another variable k here. We will check ith value and the jth value in the array b and c, and the smallest value is moved into the array a at the kth location. At that moment, if the ith value is moved, then we will move I to the next location, and then at the same time we will move k to the next location, and then we will again compare the ith value and the jth value, that is 3 and 2, and the smaller value will be moved to the array in the array a at the kth location. So 2 is moved here, and then we will move j to the next location, and then we will move k to the next location. Now what will happen now? Next we will do the ith we will compare the ith location and the jth location values. The 3 and 4, the smaller value will be moved into the array a, and now I will be moved to the next location, and as well k is moved to the next location. We'll do the same here. We will get 4 here, and we'll move j to the next location and k to the next location. Then we will compare 5 and 6. So 5 will be moved here, so I will be moved to the next, pointing to the next location, and j at the same position. So then 9 and 6 will be moved to array a, so, and the k is incremented to this location. Then we will compare j is moved to the next location. Then we'll compare 8 and 9. So 8 will be moved and j will be moved to the next location. So 8 is moved here and the k is moved here. Now there are two ways now to proceed on this way. Either we just move, we will check that which array is finished, and then we will move the other array, or the algorithm that is in the Corman's introduction to algorithm is given that author adds another value infinity at the end of the location at the arrays, like this one, and when j moves to infinity, it means whatever will come on the other side, it will be moved to the array a. So if you compare 9 with the infinity, so definitely 9 is going to be this one. The arrays fill, then we will stop here, and all the arrays values are sorted in this part. So this is how the sub arrays are merged together, so that the needed sort array is basically the sorted one. Now moving toward the actual algorithm of the merge operation. So this is not merge source, sorry, this is merge from in the array a, starting from s to m. That would be the one sub array, and the second sub array would be starting from m plus 1 to end. That was shown in the previous figures in the model that we designed on the whole page. First of all, we are going to calculate the size of the first sub array, and this is the size of the first sub array, that is the left sub array, and this is the size of the second sub array, that is the right sub array. After that, we will create two copies of these sub arrays. First of all, we have to create two sub arrays b and c of the size n1 plus 1 and n2 plus 1, and then we will copy the left sub array into b, and we will copy the right sub array into c. These are two simple for loop statements. I think hopefully you can write it. And this is the word what we added at the end, the infinity at the last location. So we have added the infinity at the n1 plus 1th location and n2 plus 1th location, so that whenever the one array finishes, the other all the elements of the other array move to the array A. Then we are initializing I and j with the 1. Now starting k from s, because our array is going to start from s, so this loop is starting from s towards the end, so it is going to fill the whole arrays like just like this one. But at this point, at this time, the starting point is s and the ending point is e. If there is a comparison between the two elements, the ith element and the jth element. If the ith element is the smallest, then it is going to move into the array A at location k, and the I would be incremented by 1. And if the jth element is the smaller one, then j is going to be moved into the array A at kth location, and j is incremented. The k is automatically incrementing in this loop because this loop is moving from s to k, so k is automatically incremented. Now moving towards the analysis of the algorithm. So first we have to calculate the individual cost, repetition, and the total cost. So the individual cost of this line would be C1, this is C2. Create two sub arrays, so this is a declaration statement, so there's no time complexity of this one. Copy values would be C3, C4, this is C5, C6, C7, C8, C9, C10, C11, C12, and C13. The repetition, this is going to be repeated only once, so this is again repeated only once. Okay, so line number 4, this is going to copy the whole array, so this is it would be of time complexity n. Okay, so it's also of n by 2, both are the half sub arrays, so n by 2 and n by 2. Okay, and then this would be big O1, sorry, it's constant time operation. Repetition is 1, so repetition is 1. Here again repetition is 1 for start to end. So if we consider it our array of size n, so this is going to be n plus 1. So this is going to be n, so n times for true and 1 times for false. So this is going to be executed for the true times of the line number 9. So if we go to write 10, 11, 12, 13, and 14. And because then part and else part, I have already told you how we have to handle it with the k variable. So hopefully you can recall that lecture where k varies from 0 to 1. So this is again nk, so this is going to be 1 minus k into n, and we have to mention the range of k. So this is again 1 minus k, where k ranges from 0 to 1 times n. And then we are going to multiply all these ones, so this is going to be c1, c2, c5, c6, 10, this is nk, c11, 1 minus k, and c12, this is 1 minus k, and c13. So now we are going to add all these values that are mentioned here, that is in the total. So the total running time of this algorithm would be C1 plus C2 plus n by 2 C4 plus C5 plus C6 plus C7 plus n plus 1 C8, then NC9 plus NK C10 plus NK C11 plus 1 minus K times NC12 plus 1 minus K NC13. However, you can do the simplifications and finally we can get the answer. So we can see there is only constants like C1, C2, C5, C6, C7, here C8, and here C again, and there is no and then there are few terms of n, we can see here, and there is no term greater than n, so we can write it as an plus b, and where a is equal to this and b is equal to this. So you have to do it yourself, simplification, and then write the values of what is a and what is b. So we can say this is a linear time algorithm, and we are just talking about only the merge, not the merge sort. So and the next we are going to calculate the time complexity of the merge sort, the whole one. So we have calculated the time complexity of the merge. We can represent it in asymptotic notation as theta of n. Okay guys, now so here is the merge sort algorithm, and if we just go roughly, so this is going to be executed once, so we can calculate its time complexity. Also it is going to be repeated once, so it would be C1, C2, C3, C4, C5. We have already seen that the merge sort's complexity is theta of n, so we can easily mention it here. So it should be here, so theta of n, so it is going to be repeated once. So if it is theta of n, so it is repeated by 1. So okay, so sorry guys, so this is not theta of n, so I just mixed up with the merge one. So this is theta of n times, and this is going to be repeated once. So these are the two parts which cannot be calculated. If we are using the time, if the time complexity of this algorithm is t of n, that we need to calculate it, then these are the sub problems of this same problem. So if its time complexity is t of n, then its time complexity would be t of n by 2. So this is going to be t of n by 2, but we don't know what is the time complexity, what is the value of t of n by 2. So it's going to be, so the cost of divide, so that is theta of 1, the cost of deviant, so t of n, two sub problems of size n by 2, plus t of n by 2, the two problems of size n by 2, and then the cost of the conquer, that is theta of n. If we combine all these ones, So it will become 2t of n by 2. So two sub problems of the same sizes, so we can add these two problems. So there are two problems of size, each of size n by 2 here, you can see here. Plus if we add theta 1 and theta constant time and linear time, so then it is only of theta of n. So this is the recurrence equation of merge sort. So for divide and conquer algorithms where the implementation is of we're using the recursion, the running time or the time complexity, we need to find first the recurrence equation. So this is the recurrence equation. After that we will apply there exist different methods through which we can solve this recurrence equation and find our time complexity of this algorithm. For this algorithm, for the merge sort, we are going to use tree method to calculate the time complexity of this algorithm, that is merge sort. Okay, so first of all, let's see how. First of all, I will try to teach you how to calculate this tree. So I will do it step by step in every different figure. So first of all, we need to calculate T of n. Now we apply this equation on this T of n. So if you need to calculate T of n, then there would be a cost of theta of n that would be applied, and there would be two sub problems of size n by 2 and m by 2. So it means if you calculate T of n, then you have to face a cost of Cn that is equivalent to theta of n, and then there would be two sub problems of size n by 2 and n by 2, that is T of n by 2 and T of n by 2. Now when you go for the solution of these two problems, you put n by 2 as in place of n. T of n is equal to T of n by 2 plus theta of n. So just replace n with n by 2, so you will get T of n by 2 is equal to T of n by 4 plus theta of n by 2. Just replace these values with these ones, so you will get C of n and here its cost would be C of n by 2 and C of n by 2, and then there would be two sub problems, new sub problems of T of n by 4. So 2 is missing here and 2 is missing here. T of n by 4, T of n by 4, there is T of n by 4 and T of n by 4, and then we just keep on doing at 2 or 3 levels, and then we will start calculating the time complexity. Now guys, we keep on doing till we get T of 1. So we are dividing n by 2, 2 by 4, 4, then 8, then 16. So then the value of n is reducing in a binary form. So finally you will get this kind of expression, and that would be equivalent to theta of 1, theta of 1, theta of 1, and theta of 1. So this is, you can say this is a binary tree, and this is a obviously this is a high balanced binary tree. So let's calculate the time complexity at each level. So this is going to be C of n. So this is C of n by 2 plus C of n by 2. that is c of n. So here it is c of n by 4 plus c of n by 4 plus c of n by 4 plus c of n by 4 is equal to again c of n. And as if in the same way we can see that the time complexity at each level is c of n. So it means if we add all these time complexities, we can get our overall time complexity of, that is t of n, c of n plus c of n plus c of n plus so on up to c of n. And then the major question is how many c of n's are there? The obvious question answer is the number of levels. So in a height balanced binary tree, this is always log of n. So that means there are going to be log of n cn's. So this makes it cn log of n, and this is equivalent to theta of n log of n. So this is the time complexity of merge sort. In the best case, in the worst case, in the average case, it always behave in the same way for any kind of data, and so it always behave as n log of n. So but the major flaw is, so the major flaw is it is not in place. So that means it need extra space. And how much space is required? And that is equivalent to your array, that is theta of n. So guys, hopefully you will be getting all this one. So if you need have any query, please don't hesitate to ask it. Do ask it right now, and let's do the best for the rest of the time. So this is what I was writing here. It was not in the screen, sorry for that. So hopefully guys, we will meet in the next lecture. So thank you very much. Allah Hafiz.